Hi everyone, my name is Mertens. I'm a grad student at the University of Hawaii. Welcome to my presentation of my paper, Comparative Analysis of Uncertainty Quantification Models in Active Learning for Efficient System Identification. Why do we want to do active learning for system identification? In our lab we work in space exploration, more specifically with rovers. And those rovers we want to deploy in unknown environments where we generally don't have a lot of training data. So we're trying to design algorithms that work well with limited data and a minimum number of samples. And to this end, I've compared different uncertainty quantification models that we can use in our active learning algorithms to perform efficient system identification. How does system identification or active learning for system identification generally work? We have this iterative algorithm where we train either a Gaussian process or a Bayesian neural network in each iteration. And what's nice about these models is that they give us an uncertainty quantification alongside with their prediction. And we can then use this uncertainty quantification and query the models and ask them, out of all the possible inputs I'm presenting you, which ones are you most uncertain about? And then we select those inputs because we expect the model to gain the most information from being trained on those inputs down the line. We then feed the inputs through our dynamical system and measure the system outputs. And with the outputs we can build input-output pairs where our inputs are the state variables at time t, and if it's an actuated system, also the actuation, and our outputs are our state variables at time t plus 1. And in doing so, we can teach our models to predict how the system forward propagates in time. And we keep doing this iterative process until we reach some stopping condition where we say that our models are sufficiently well trained for whatever application we care about. Let's look at our acquisition function. So our inputs is a vector of our state variables and possibly also our actuation. And since we're using probabilistic models, our outputs will give us a distribution, or the model will give us a distribution over our outputs with a mean and a standard deviation. And we can then use this standard deviation to find the output that has the maximum standard deviation, which represents the maximum uncertainty. How does the convergence criteria look like? Our convergence criteria is inspired by the settling time from control theory. We say that an error has to stay below a certain threshold for 20 consecutive iterations, and then we see our model as converged. How do we calculate this error? Whenever we query the models over our inputs, we get a uncertainty which we use to select the inputs, but we also get a prediction. So we have a prediction of our output, and when we then feed the input through a model, we will see the actual output, and we can compare the two to calculate a relative root mean squared error, which we use as our convergence criteria, which has to remain below a threshold of 2%. We've looked at 3 different uncertainty quantification models, Gaussian processes, which are kernel-based methods. We've looked at RBF and Mertens kernels, and Gaussian processes are generally the benchmark and the most commonly deployed uncertainty quantification models. Ensemble neural networks, we train multiple neural networks in parallel for those, and each neural network predicts a mean and a variance. And we can then average over those predictions, but also use the disagreement between the models at the same time to get a final distribution over our outputs with the mean and the variance, and the variance we use as a measure of uncertainty. For Monte Carlo dropout neural networks, we only have one model, where each neuron is associated with a certain dropout probability. And during inference, we run an input thousands of times through our model, and the outputs will all be different because different neurons will be active and inactive, which allows us to generate a distribution over those outputs. And the standard deviation of this distribution we can again use as a measure of uncertainty. We've looked at 5 different dynamical systems: the actuated pendulum, damped pendulum, double pendulum, Lorentz attractor, and the two-tank system. We have systems with different characteristics. We have chaotic systems, non-chaotic systems, passive and actuated systems, and systems with different input and output space dimensionalities. We also have more and less complex systems, which will be more obvious if we look at the ODEs that describe these systems. The damped pendulum and actuated pendulum can be described with just one differential equation. For the Lorentz attractor and the two-tank system, we need a few more equations, and the Lorentz attractor also has a slightly higher state. But things get really interesting if you look at the double pendulum, where we have 4 variables in our state vector, and we also have these really large equations that are highly nonlinear and quite complex, and we expect our models to require a lot more training data to be able to replicate these dynamics efficiently. Okay, I want to give you a simple example of how active learning can look like, and for this we're going to look at the phase portrait of the damped pendulum. The phase portrait describes the evolution of trajectories in state space. State space in this case is theta and omega, so the angle and angular velocity of the pendulum. The colorful arrows are the predictions of our model, and the white arrows in the back are the ground truth, and the red crosses are the training data points that our active learning algorithm selects. And if our model is able to replicate this phase portrait, it should have learned the dynamics of the system. So if we let this run, we see that the algorithm only takes about 12 iterations, and then our model converges to a very accurate solution and is able to replicate this phase portrait almost perfectly. We have evaluated our different models across 3 metrics, which are samples until convergence, runtime until convergence, and accuracy upon convergence. And each experiment we have rerun 10 times and averaged over those 10 trials. And we have this large table in our paper that summarizes all our experiments. And we've also reported means and standard deviations for all of them. And in the next couple of slides, I will try to condense all this information into smaller bits and pieces. The optimal model we've seen as the one that excels in at least 2 out of 3 of these metrics. And for 4 of the 5 models, this was a Gaussian process model. For the double pendulum, however, we've seen that the ensemble neural network was the most sample efficient and also the most accurate model. So it really seems like that for the more complex system, a ensemble neural network is a good alternative, but for the more simple and low-dimensional systems, Gaussian processes really excel. And we can see this really quite well if we look at the 2 graphs on this, the 2 figures on this plot. On the left side, we see the double pendulum. On the right side, on the left side, the damped pendulum. On the right side, the double pendulum. And what we see is the test error over the active learning iterations until convergence. For the damped pendulum, we see that Gaussian processes converge to really accurate solutions with a minimum amount of training data. And we've seen fairly similar results for 4 out of the 5 systems where Gaussian processes do really, really well. But on the right side, we see that the ensemble neural network only requires about half of the training samples that the Gaussian processes do and still converges to a more accurate solution. What we've also seen is that the Monte Carlo dropout models had a poor performance across almost all systems and all metrics. We believe that the reason for this is that we're losing information when doing dropout, and since we are acting in the latent space here, losing information really hurts your performance, which the other models don't have to deal with. One interesting training mechanism that we've looked at is what we call continuous training. In continuous training, we initialize the weights or the parameters of our models with the learned parameters of the previous active learning iteration. So for our neural networks, this will be the weights and biases, and for the Gaussian processes, the learned length scales. And what we've seen is a huge boost in performance, specifically for the ensemble neural networks. So for the ensemble neural networks, it really seemed to help navigate the loss surface during training to be initialized with a good solution or a better solution than random weights, and really help to get closer to the global minima that we want to converge to. For the Gaussian processes, we saw an improvement in performance in this case measured by sample efficiency for the RBF kernels, and a loss in performance for the Mertens kernel models. The reason for this is that RBF kernels represent a smoother set of functions, so they're less likely to overfit. So for the RBF kernels, we were able to find a better representation which still generalizes well by employing continuous training, whereas for the Mertens kernel models, we've overfitted for most of our systems. And for the Monte Carlo dropout neural networks, we also saw a decrease in performance. Those models were not working really well to begin with, so we were initializing our models with bad solutions, which didn't seem to help. One thing we've also looked at is learning consistency, so how consistent were the 10 individual trials of our experiment. What we've seen is that Gaussian processes were really consistent within our experiments, and for example the ensemble neural networks had a much larger spread. The reason for this is that all models have some randomness because we selected the first 2 training samples randomly, but the ensemble neural networks have a much higher inherent randomness. This is because we have random initialization of the weights, and then we forward propagate this randomness by doing stochastic gradient descent. If people want to reduce this variance, they can simply include more models in the ensemble at the cost of compute time. To conclude, no model works best across all systems and metrics. Gaussian processes are a really solid choice for the more simple systems with less complex dynamics, but for high-dimensional and complex dynamics, ensemble neural networks, especially with continuous training, are a really good alternative. And Monte Carlo dropout neural networks we don't recommend for active learning for system identification, especially when acting in the latent space. For future work, we're currently looking into extending this to experiment design, where we strategically select the initial conditions of simulations of dynamical systems instead of learning the dynamical system itself, and also into hyperparameter optimization for the ensemble neural networks. The problem with this is that it's non-trivial over which data sets and for what losses you're optimizing. The data sets are constantly changing, and there can also be different objective goals, and this is another research project that I'm currently looking into. So thank you very much, and thank you to the AI Institute in Dynamics for funding this work.